Hello everyone, so in this particular video we are going to look at the topic of tensors in PyTorch. So this video and the next video are going to be theoretical and they will form actually the basis of the entire PyTorch as to how computations happen and how backpropagation happens and how the models are run and trained. So this video and the next video are going to be the basis of that. So without any further ado, let's get started. But one thing that I want to tell is if you want to have a one-to-one discussion for a couple of minutes on your projects or anything related to computer science, please look at my Fiverr page. The link is in the description. Okay, so what is tensor in PyTorch? Well, tensor can be anything, like it can be a collection of numbers in different dimensions or a single number also. For example, you can have a list, you can have a matrix, or you can have numbers arranged in any dimension. In PyTorch, you call that as tensors. So yeah, like any numbers, any dimensions, that is a tensor. What it is used for? Obviously it is used for computations, it is used for forward propagation, it is used for backward propagation, and basically everything in PyTorch happens through tensors. It's just like numbers, PyTorch understands tensors as numbers. So the thing is that it is used in the computational graphs, and that is the third topic. What are computational graphs? Computational graphs are basically used for training algorithms in PyTorch. So the four aspects that we are going to look in this video, no, two of them in this video and two of them in the next video. So the first one requires grad and the second one is leaf are the two of parameters that we are going to look in this video, and the next two we are going to look in the next autograd video. Okay, so let's assume a simple equation. Let's say z equal to x square plus 4y. So this is going to be a very simple equation, and if you want to find this expression and evaluate this expression in PyTorch, you have to do it this way. So x will be described as torch.tensor. So a single value is also a tensor. A list can also be a tensor. As I said, matrix or 3-dimensional, 4-dimensional, any dimension, n dimension, whatever numbers you are using in PyTorch is a tensor. And then you have y equal to torch.tensor 5. So I have assumed the value of x to be 3 and value of y to be 5. And when I say z equal to x square plus 4y, this particular expression is evaluated and you get answer as 29. So x square, x is 3, 3 square is 9, and 4 into y is 5, that is 20. 9 plus 20 is 29. Now my question is, can we differentiate this? The answer to this is no, because we have to do something else to be able to differentiate it, and that will be the topic of the next slide. However, we cannot differentiate it. So when I say differentiation, I mean dou z by dou x, which in this case I will just say dz by dx. So let's say you want to find out dz by dx. Can you do it? Well, answer is no, because right now PyTorch will not be able to do the differentiation. Now the question is, why do you need to do the differentiation? Well, the answer to that is backpropagation. Backpropagation is an algorithm that trains neural networks, right? So in order to do backpropagation, you need something called as the chain rule. Well, backpropagation is nothing but chain rule, and chain rule depends on whether the functions that are in the propagation, in the forward propagation, forward pass, are differentiable or not. So obviously these functions are differentiable, and hence we will be able to use PyTorch for backpropagation, and for that these functions require something. Now how to make it differentiable? Right now it is not. So to do that, we use something called as requires grad. This parameter has to be set to this parameter has to be set to true. So I haven't made any change. I have just said this x was there in the last slide. You can see x equal to torch.tensor 3. What I have done is I have just added requires grad with underscores and put it to true. Similarly for y, requires grad underscore and then you have true, and done nothing else. Then what we will do, we will define the equation and find the answer. Torch.tensor thus 29 will be the answer. However, to get the backward pass, that is to get dz by dx, I will not say dou, I'll say dz by dx, which is in this case will be 2x. So if you differentiate this equation keeping y as constant, if you differentiate dz by dx, you will get 2x, which is 2 into 3, that equal to 6. Similarly, if you treat x as constant, you will get dou z by dou y or dz by dy equal to 4. Now how you are going to do this? you are going to simply write after this line, after z equal to x square plus 4y, you are going to put one more line, that is z dot backward. Now if you remember in the linear regression or logistic regression or the breast cancer data set, we used loss dot backward. It is similar thing. However, here we are using z as our variable, there we used loss as our variable, but the context, the concept is basically the same. Okay, so what it will do is it will find these derivatives, the value of these derivatives. Okay, so how we are going to use it and how we are going to extract it is something for the next video. Okay, so till here we are done. Then we need to understand that how we are going to evaluate it. So when I said z equal to x square plus 4y, what you did is in place of x you put the value of 3 and in place of y you put the value of 5, and then you evaluated and got z equal to 29. However, PyTorch doesn't simply do like that. What it does is it tries to break as many expressions are there into smallest possible expressions. So how can you break it? So it says, okay, there are three operations. One is the square operation, one is the addition operation, one is the multiplication operation. So the PyTorch thinks, how can we divide this into more smaller expressions? So it says, why don't I take the square and give it another intermediate variable? This PyTorch does for itself. You don't have to set it. PyTorch will do it for it will do it inside its own code. And then it will look at the second expression. Okay, 4 into y. It will break that also into break the whole expression, the second one, and call it t2. Okay, so all the operations have been made into smaller ones. Now the third one was plus. So it says, okay, now what I can do is I can say t1 plus t2. So this is a smaller expression, this is a smaller expression, and this is the third smaller expression. And once you combine all of three, you get the final expression. Now the question can be, why PyTorch does it? Well, the answer is to build the computational graph. What is computational graph? That is for the next particular slide. Okay, so at least this is clear that what you are going to do is basically you are going to take the expression, and what PyTorch does is it takes the equation and breaks it into smaller pieces and then further aggregates it at the end. That is what it does. Okay, so this was our expression, and this is the computational graph. And let me go very slowly in this, because this is going to be very important to understand the backward pass, which is back propagation, which is the core of PyTorch or any deep learning library. So you have this expression. What you started with is x and y. I have written the values in the brackets, in the curly brackets, for reference. Okay, so what I have done is initially there was x and there was y. What we did is we had a power function on x. So what it does is it gives a power function and the value is t1. This t1 is given implicitly by PyTorch. We did not specify t1, and it calculated the value as 9. Simultaneously, what it did was 5 was also there. Y equal to 5 was there. So what it did, it applied a multiplication operation and it found t2, and the value of that was 20. 4 into 5, that is 20. Now after the two expressions, there was another one. What happened? It added both of them, the results of t1 and t2, and it got something as z, 29. Till here we are fine. Now what happened after that was PyTorch always adds another variable and says that it is equal to this. Okay, so the final variable that PyTorch added, w, we did not add it, PyTorch added for itself, and it said the value is going to be the same, that is equal to z, and it will do this in all the cases. Okay, so PyTorch adds the last part by itself so that it can make backpropagation easy. It can actually do backpropagation, and that is the reason why this one is added over here. So I hope you understood the computational graph, and this is very important, because in the next particular video we are going to use this to do backpropagation. Fine. So very simple. Whatever elements were there, you have it. You did the expressions, you did the operations, and then you got the intermediate results. Then you did another operation, and then you got the final result. And then PyTorch added one more of its variable at the end, which is equal to the last one that we found. Now this is the last slide of this particular lecture. Leaf node. Now I talked about requires grad and is leaf, if you remember in the start, if you remember over here. Requires grad was the first one that we dealt, and now we are going to do is leaf. Now if you look at is leaf, what is this one saying? Now if you remember the tree data structure, you had something like a root node, and then you had certain intermediate nodes, and at the end we used to say that if a node does not have any more child node, we call that leaf nodes, right? Here the case is a bit different. Leaf node is almost, you can say, it's like an independent node. Now it is not that it is always independent. I mean, you can make it independent by using, if you remember, you used to use loss.detach. That was making that particular variable loss outside of the computational graph. We were using it outside of the computational graph. So let's say if a node is there and it is not being derived. See, T1 has been derived by X, but X was not derived by any other node. T2 has been derived by Y. Y was not derived by any other node. Z was derived from T1 and T2, which were in turn derived from X and Y. However, Z was derived from this. However, X and Y themselves were independent nodes. So let's say, you can say a leaf node is an independent node which has not been derived from any other expression or operation. So the way you will use it is x dot isLeaf. We are going to do all of that in the next particular video. So I hope this was clear, and this is half the tutorial. In the next video we will be looking at AutoGrad, that will be helping us in the differentiation of the computational graph and finding the gradients and backpropagation for using in backpropagation. So thank you very much, and wait for the next video.